So let's discuss the Foucault pendulum. The first thing we're going to need, of course, as always, is a picture. So here I've got my x-axis pointing east, my y-axis pointing north, and my z-axis pointing up. And I've drawn the pendulum swinging back and forth at in some plane between the x-plane and the y-plane, or a plane that goes through x and z and a plane that goes through y and z. It's in some plane between those. So now let's figure out what the components of things are going to be. So we'll add to our drawing. I've added in the x-coordinate, the y-coordinate, and the tension force, and drawn in the x and y components of the tension force. So now let's write down Newton's second law in this rotating reference frame for this system. We have m times the second derivative of the position with respect to time is equal to the tension in the string of my pendulum plus mg naught, which is just the gravitational force at this local region in space, plus m omega cross r cross omega, that's the centrifugal force term in the non-inertial rotating frame, plus 2m r dot cross omega, and the 2m r dot cross omega is the Coriolis term. Now, as before, we can take this mg naught, this gravitational term, and the centrifugal term, m omega cross r cross omega, and instead of having mg naught, if we combine the centrifugal effect with the gravitational effect, we get the effective g without the zero, not g naught, but g. And so we can rewrite what we have, where we combine the gravitational term and the centrifugal term in mg, and the rest is still the same, t plus mg plus 2m r dot cross omega. Now let's let's draw in the angle that the string on the pendulum is swinging at relative to the z-axis. So we have this angle beta, and since beta is assumed to be small for this problem, we could say that the z component of the tension in the string, which is equal to t cosine beta, when beta is small, this is just going to be equal to t, the total tension. So the total tension and the z component are about equal when beta is small. Also, for slow oscillations, we have v is going to be small and omega is small, and so this Coriolis term will be small relative to the mg and the t terms, and r double dot will also be small. It won't be swinging very quickly, and so the magnitude of t is going to be about equal to the magnitude of mg. Or rather, since g is in the z direction, we can write that tz is about equal to mg. So because of the previous thing, that tz is also about equal to t, we have t is about equal to mg. The other thing to note is another way to express tx and ty, where we use this drawing. So from the drawing, we can see that tx over t's magnitude, or at least the component tx over the magnitude of t, is going to be given by minus x over L, because geometrically, x over L has the same geometrical relationship as tx over t. And so we say that Tx over T is minus x over L, the minus sign, because these tensions, this tension forms a restoring force. And the same thing for the relationship between Ty and T and y over L. We have Ty over T is equal to minus y over L. So rearranging these two conclusions, we get that Tx is minus, well, T we just said was about equal to mg, so Tx is minus mg x over L. And here we have the Ty is minus Ty over L, but again, T is about equal to mg, so we get Ty is minus mgy over L. The other result that we're going to need is for this 2m r dot cross omega, we're going to need to evaluate r dot cross omega, but we've already done that previously. So from equation 9.52 in Taylor, we evaluated r dot cross omega to be y dot omega cosine theta minus c dot omega sine theta for the x component, minus x dot omega cosine theta for the y component, and x dot omega sine theta for the z component, where x is east, y is north, and z is up. And in this expression, we are assuming that the direction of omega is given by a line that goes from the center of the Earth through the North Pole and straight upwards from there. So in this scenario, omega has a y component, a northern component at the location on the Earth where the experiment is being done, and it has a z component which is toward the zenith at the location where the experiment is being done. So omega projects onto y and z, but it doesn't project onto x. So here you have the sketch that we used before to evaluate r dot cross omega. Omega points straight up from a line that goes from the center of the Earth to the North Pole and straight up would give us omega. And then y is at the location where we're doing the experiment, the direction of north along the surface of the Earth, and then z would be up toward the zenith at the location where we do the experiment. And of course, r dot would be given by, the position of some object close to our coordinate system. So there'd be some object close by. So going with the drawing that we've made, and so this is the drawing we used. This was our resulting Newton's second law in this rotating reference frame. This was the r dot cross omega expression, which I alluded to the derivation of previously using the picture I just described. And then we have our expressions for Tx and Ty. We can now write down the component equations corresponding to this Newton's second law equation. So, so here I have, instead of mr double dot, I have mx double dot, t goes to tx, plus 2m, and then I plug in the x component of r dot cross omega, which is y dot omega cosine theta minus z dot omega sine theta. Except in this scenario, we have that z dot is very small, so z is not changing very much. So we get rid of this whole second part of this term. And then for the y equation, we have my double dot is equal to ty plus 2m, and then the y component was minus x dot omega cosine theta. So that's written in here. And so then rewriting the x dot equation, we're given mx double dot. We know that tx was minus mgx over L from this result over here. And then we write down the rest without the little term that we're counting as 0. And so we have mx double dot is minus mgx over L plus 2m y dot omega cosine theta. Now let's cancel the m's. And rewriting the y dot equation, we again have my double dot equals mgy over L, plugging in for t sub y, minus 2mx dot omega cosine theta. So we have that one. And so now we're going to cancel out the m's in this expression. So let's rewrite what we have so far. And notice that we've canceled out m's everywhere now. And we remind ourselves that theta is the colatitude. So omega cosine theta is omega z. And so we can make that substitution for the ends of these two expressions. And doing so, we pick up this 2y dot omega cosine theta becomes, when I move it over to the left-hand side of the equation, minus 2 omega z y dot. And I am also moving over the minus gx over L to the other side of the equation. So that becomes plus gx over L. And so now, since everything's been moved over to the left, all of that's equal to 0. And then we do the same thing with the y. We now have y double dot. We have plus 2 omega z x dot from over here. And then we have plus gy over L because we've also moved this term over to the left-hand side. And again, now since we've moved everything to the left, that's equal to 0. Furthermore, since g over L is omega naught squared, we can rewrite this whole expression as x double dot minus 2 omega z y dot plus omega naught squared x equals 0, and y double dot plus 2 omega z x dot plus omega naught squared y equals 0. And so we have our differential equations to solve. So let's write those equations on the next slide. So this is what we're left with at this point to solve. Now we're going to use the same complex numbers approach to solve these equations, these two equations, as we used to solve for a charged particle in a magnetic field in an earlier chapter. So to do that, we have to create a complex function. That is, we're going to create a function eta, which consists of an x equation and a y equation. These are our solutions for x and y. And the y is going to be multiplied by I to put it on the vertical imaginary axis, and the x is along the real axis of the complex plane. Then if we take time derivatives, we just get eta dot is x dot plus I y dot, and another derivative would be eta double dot equals x double dot plus I y double dot. So we're going to use these new definitions for eta to recast these coupled differential equations. We're going to take the second of these, the y double dot, or the y equation, and we're going to multiply the y equation times I and add it to the x equation, and then see if we can plug in so that instead of having x dot, x double dot, y dot, and y double dot, we have everything in terms of eta. So as I said, we're going to do the top equation plus the bottom equation times I. Let's see what we get. So, as I said, adding x equation to I times the y equation, we'll get an x double dot plus iy double dot. Then we have plus 2 omega z, and we have an ix dot minus, from the up top we have the minus y dot, so we have ix dot minus y dot, and then we have the plus omega naught squared x plus iy. And so we've combined the equations, as I've said, and all of that top equation plus I times the bottom equation is equal to 0. Now let's take this expression. We have an eta double dot here, and we have an eta here. But here we have ix dot minus y dot, so that is not eta dot. But I can factor this I out front. And so let's do that. Let's factor the I out front. If I factor the I out front, so I've taken this I and I've placed it here, I'm okay, I can just write x dot, but I've got to get minus y dot out of the whole thing, which means that instead of having minus y, if I have plus I y dot here, the plus I multiplies with the I on the outside and combines to make minus 1. So then when I multiply this out, I'll get back the minus y dot I started with, so long as I change the minus sign to a plus I. So now if I do that, then I'm in a good position, because now I have x double dot plus iy double dot. I have x dot plus iy dot and x plus iy. I can write all of this in terms of this definition for eta, the complex function. And so we do that, and we get eta double dot plus 2I omega z eta dot plus omega naught squared eta equals 0. Let's rewrite that on to the next slide. And our standard way of solving this is to guess a solution of the form eta of t is equal to e to the minus I alpha t. Now, this is a second order ordinary linear differential equation that is homogeneous, and so we expect two independent solutions. So in the end, we're going to expect two different values of alpha to give us our two independent solutions, which make up the total solution. So the next step is to take our trial solution and plug it into this differential equation and see what we get. When we do the second derivative of eta double dot, we're going to pull down 1 minus I alpha with the first derivative, and then another minus I alpha with the second derivative, and that's going to give us minus I times I times alpha. So minus I times minus I, the minus and the minus make plus, but I times I makes minus 1. So that makes minus alpha squared. So let's see that come out. I have the minus alpha squared eta. And then for the middle term, eta dot, I'm pulling down just minus I alpha. So I have minus I alpha times eta times the coefficient 2I omega z. That's here. And then for the last term, I just have the no derivatives of eta, so it just is again plus omega naught squared eta, and the whole thing is equal to 0. And so now what I can do is divide out the solution eta, and I'm left with this characteristic equation minus alpha squared. I have an I here and a minus I here, and minus I times I is plus 1. So I have plus 2 alpha omega z, I have that, and then I have the plus omega naught squared, and all of that is equal to 0, And I think we're beginning to see from this quadratic equation that I will get two solutions for alpha. And the way I'm going to get these solutions is to complete the square on the left-hand side. First, let me just multiply by minus 1. So I have minus alpha squared goes to alpha squared, plus goes to minus, and plus goes to minus. And so now I've got this characteristic equation, and I want to complete the square here. So completing the square, I get alpha squared minus 2 omega z alpha plus, here I'm adding in plus omega z squared to complete this square, right? I take 1/2 times the coefficient squared, and then I have, since I added in an omega z squared here, I have to subtract off that omega z squared, and then I still have my minus omega naught squared. These guys are coming along for the ride right now. And so I get, on the left-hand side, I have alpha minus omega z quantity squared. That's these first three terms combined. And then I move these two terms, these two constant terms on the right, I move them to the right-hand side of the equation, and I get omega z squared plus omega naught squared on the opposite side of the equation. Now if I take the square root of both sides, I get alpha minus omega z is equal to plus or minus the square root of omega z squared plus omega naught squared. So let's rewrite that on the next slide. And we're going to solve for alpha. So we put this omega z on the other side, and we have alpha equals omega z plus or minus the square root of omega z squared plus omega naught squared. Now since in this problem omega z is very small, the angular frequency of the rotation of the Earth is very small relative to the natural frequency of the pendulum, and so this square root stuff, the omega z is very small compared to omega naught, so I can neglect this omega z squared, and then I have the square root of omega naught squared, which is just omega naught. So we're left with alpha is about equal to omega z plus or minus omega naught. And so then my solution for eta is just a constant c1 e to the minus I omega z minus omega naught, that's one of these two solutions, times t, plus another constant, complex constant, c2 e to the minus I, and now I have omega z plus omega naught, that's the other independent solution, times t. So there, now I've done it. I've solved for eta. Now the nice thing about eta is, just as in the case of the charged particle in the magnetic field, this eta plotted in the complex plane is actually the xy plane, and so it will show me a bird's eye view of the motion of the pendulum. So let's rearrange this solution a bit. We'll take out the slowly changing part, the omega z part. We'll factor that out of both these terms, and we will consider specific initial conditions where you pull out the pendulum along the x direction and start it from rest pulled out at some angle, and see how it evolves over time. So we have, as promised, we're factoring out the omega z part, so we have e to the minus I omega z t, and then we write out what's left, which is c1 e to the I. Here I have minus I and minus 1 omega naught, so that's c1 e to the I omega naught t plus c2 e to the minus I. I'm missing an I here. I think I can put it in just by hand, I believe, quickly. Sorry. I'm going to write that in. Okay, that didn't look so good, but at least it's there. So I have C1 e to the I omega naught t plus C2 e to the minus I omega naught t. And so I've rewritten my solution, and at t equals 0, we're going to let x equals a, as I just said before. We're going to let y equals 0, and vx naught and vy naught will both be equal to 0. And now we want to evaluate this solution under these initial conditions. And so this is our solution. Eta, again, is equal to what I've read off before. And so at t equals 0, we have eta at time 0 is just plugging in 0 for t everywhere. I'd get C1 plus C2 is equal to a, right? Because I have to get x equals a, or the position is equal to the real number a at t equals 0. And we have to do the derivative. So eta prime at time 0 is a product rule. We have to differentiate the term on the outside, which pulls out a minus I omega z, and then it's times the stuff in parentheses, t equals 0, which is just going to give me C1 plus C2. And then I have plus, and now I have the first term evaluated at 0, which is just 1, times the derivative of the inside of these parentheses, which is going to pull out an I omega naught times C1 evaluated at t0, or times this exponential at t0, which is just 1. So it's plus I omega naught C1. And then I have minus C2, because this one, when I differentiate it, I pull down a minus I omega naught. So here's the minus sign, here's the I omega naught, and I have C2, and the exponential itself evaluated at 0 is 1. So that's where I get the I omega naught C1 minus C2. Now I want to neglect this first part here because it has a capital omega sub z, and omega z is very small because this is from the rotation of the Earth, which happens on a relatively large time scale relative to omega naught. So since omega z is small compared to omega naught, say, I can ignore this term. And then when I rewrite, I then get eta prime, or eta prime, or prime here is a time derivative, at 0 is about equal to I omega naught C1 minus C2. And all of that's equal to 0, so that must mean C1 equals C2. When I combine that with the previous condition, I get that C1 plus C2 is A, but C2 is equal to C1, so C1 plus C2 is the same as C1 plus C1, which is equal to 2 times C1, and all of that has to be equal to A. And so that gives me that C1 is equal to A over 2, but since C2 is equal to C1, C2 is also equal to A over 2. So we want to rewrite our solution. For the given initial conditions we just described, we have eta is equal to e to the minus I omega z t, e to the I omega naught t plus e to the minus I omega naught t, that whole quantity times A over 2. So now I have my solution. On the other hand, I have e to the I omega naught t plus e to the minus I omega naught t. That's just 2 cosine omega naught t, and that 2 will get canceled with this A over 2, the 2 in this last piece, and so the 2's will go away, and I'll be left with eta equals e to the minus I omega z t times A times cosine omega naught t. And eta is equal to x of t plus iy of t equals e to the minus I omega z t a cosine omega naught t. And so now let's look at what happens to this solution over time. At t equals 0, this part on the outside, this e to the minus I omega z t, that's equal to 0. And I have a cosine omega naught t. I guess cosine term will go to 0 to 1, and so I'm just left with an oscillation with amplitude a, this omega naught t is going to oscillate back and forth, and this is going to kind of give me the direction of the back and forth motion, because at t equals 0, this is entirely real, right? So I'm going to look at how the swinging back and forth from a bird's eye view is going to change over time. At t equals 0, or close to t equals 0, this swinging back and forth is going to be along the x-axis, because this angle, this is kind of the angle of the swinging here, that angle is going to be omega zt equals 0. And so this thing's just going to swing back and forth over x. But it's interesting, as t advances over time, slowly, this angle through which the thing is going to swing, or the angle in the xy plane, is going to change. So here I have omega zt, that's this angle here, omega zt. And so this back and forth motion is going to happen at an overall angle of omega zt from the x-axis. And so you see that the motion back and forth is going to change direction over time. And that's the entire Foucault pendulum result. And you can see that the omega z is dictating the length of time that it takes for this plane to oscillate around how do I say it? The plane of motion is going to rotate around relative to the xy axes. And so if we remember our directions, x was east, y is north. So initially, this pendulum, if you started pulling it east and let it go, it would go back and forth east. But then over time, that plane of motion is going to rotate counterclockwise in this view about the xy axis. And so we have to remember that the angular frequency of this oscillation is a function really of your latitude, or in this case your co-latitude theta. This omega z was equal to omega cosine theta. And so the period of this rotating plane of motion is 2 pi over omega z, which is dependent on the observer's location on the Earth, their latitude, and so it's 2 pi over omega cosine theta. Taylor explains it slightly differently. He says, let's take latitude, for example, 42 degrees, which isn't too far from where we are in Pennsylvania. Then the co-latitude theta is equal to 90 minus 42 degrees, or 48 degrees. And if we look at that, that means omega z is omega cosine 48 degrees. That's about 2/3 of omega. Now, omega goes 360 degrees per day. That's the angular frequency of the Earth. And so 2/3 of that is going to be 2/3 of 360 degrees is 240 degrees a day. That's what the angular frequency would be at a co-latitude of 48 degrees. So what that means is in 6 hours, we would do 6/24 of that. So we would do 6/24 or 1/4 of 240 degrees. So in 6 hours, we'd swing through 60 degrees. And so in a science museum, where you've got one of these giant Foucault pendula, over the course of about 6 hours, you'll see at the latitude of Philadelphia or New York or someplace like that, you'll see a significant change in the plane of motion due to this Coriolis effect on the Foucault pendulum. And so we see that the Foucault pendulum, this really awesome, cool thing, is readily explainable through this non-inertial reference frame analysis.